Omni Labs, which has developed workflow automation, and he is also a Google developer expert for cloud and machine learning. If you guys have any questions, we'll have chances to answer them at the end, and go ahead and put those into the chat.
Awesome. All right. I'm gonna get started then. Nice. So hello, everybody. Thank you for coming in. Everybody can still see my slides, right? Perfect.
Yeah.
Awesome. Okay. So today we're gonna go through a deep dive on what is GenAI, what is machine learning, and we're gonna end up with way to have some better understanding of what GenAI is and how you can start using it. But before we get there, we need to clarify some basic terminology. Also, I like my sessions to be very interactive. So if you have at any point any questions, I actually don't know how you're going to do questions, but somebody can keep asking me questions and I'll keep replying to the answers. So as long as you have questions, it will be fine. You can keep asking me. Okay.
Yeah, any questions, go ahead and put them in the chat and then I'll read them aloud.
Awesome. Perfect. Thank you, Pearl. Okay, so from the beginning, we will start with artificial intelligence and machine learning. What is the difference between these two? So AI, we have had AI for a long time. In 1960s to like 90s, we had AI, and we have seen books about that. We have seen movies around that. The reason that AI still existed at that time because AI was built using handcrafted systems. So we had these experts who would come in from these different groups. They will come together in a place. So like NASA and NOAA did this together where they built these expert systems to predict the weather. And like, I'm sure there are more of those where they had like these amazing scientists and everybody, like experts from different fields come in together and build this model that was used to do a task. I know some trading firms who also did something similar, but that is also considered artificial intelligence. The only issue is that those were handcrafted systems. You really needed experts in those fields to come in to build anything related to that topic. Then came the era of machine learning, where rather than having experts to write the code, we had this field of, we had this ability for the machines to learn itself, where machines can use this data that we can provide it to figure out what should be the correct pathway. And these are graph-based models or tree-based models where we have essentially the machine that it learned. The learning was essentially all the if-else conditions on how to get to a solution. So that's what happened with machine learning systems. The best part here was it didn't require any explicit instructions on learning. So we already got not rid of, but redundant the experts. We didn't really need experts to build these systems. So that was machine learning, and like this is 90s, and like we are starting to see some of that come in like 2000s. That's where this is happening. Then we started seeing this thing about deep learning. I remember I was like in my last year of college or sometime, and TensorFlow got released at that time, and that was just like we saw a lot of apps around. You take a photo and you apply a Van Gogh theme on it, and you see a different photo come out of that. So all those things started coming in with deep learning, where deep learning is still a subset of machine learning. Things that change in here are how these models learn. So the models before this time were learning like each node would learn an if or else condition. But with deep learning, our nodes started to learn different patterns within the data. So to give an example, I generally keep this playground here. I don't know if you're aware about this, but this is called playground.tensorflow.org. And this is to show how or what kind of things these are learning. These are different layers of neurons that are in our deep learning model. And what we're trying to do is categorize this data between blue dots and orange dots. So we start the process and you will see this is kind of bad neural network because I don't really need 3 layers in here. But very quickly we see that it starts to learn what is happening in here. And each layer is learning different features. If I remove a layer, it's gonna lose a lot of functionality if I suddenly remove one of the layers or one of the neurons. Because at each layer, it's not learning if-else condition. It's learning different categories. And as the layers go deepen, the amount of information that it's learning becomes very complex. So at each layer, the complexity increases. So like at the beginning, we are seeing the straight lines being learned. In the second layer, we are seeing some circular part is being learned. And in here, we see a like clear distribution between blue and orange dots is being learned. So that's what deep learning started doing, where rather than each neuron learning a specific if else condition, we had different layers which started learning more and more complex information. So the thing is, this is like science fiction thing where you can make a machine which knows the whole world, but you will have to map the complexity of the whole world into the machine. That means building a machine same as the size of the world. So you can't really do that. So that was the normal machine learning models. But with deep learning, what we found that we can do a lot of complexity if each layer learns something unique, and the subsequent layer utilizes what the previous layers have learned, and based upon that, learns something more complex on top of that. So with deep learning, we started to be able to do more complex systems, more complex items. So like before this, machine learning was mostly on tabular data, and we had like very small, minimal models around how to do translation, and like that was very simple, not complex. And like autocorrect was a thing that was happening with machine learning. With deep learning, we started seeing more complex things come into play. Like we started seeing images, a lot of images that happened at that time. We started seeing video, a lot of text-based stuff happening. Then within deep learning, we have different ways of how these systems learn. So one is supervised learning, where it learns from the labeled data from the past, and unsupervised learning, where it learns from unlabeled data. The data it doesn't require any labeled data for it. So what does it look like? So this is a supervised learning example where let's say for this example, we are trying to train a model on cat versus dog images. So we put an input of data of like, we give it an image of saying, this is a cat, or tell me what this is. Model doesn't know anything right now. Model says, hey, it's a horse. So it says, okay, you probably did something wrong. And that was the prediction in here, horse. Let's compare it to what cat is, because the expected output was a cat. So you got some error. And let's take that error back into the model, and model will update itself to say, hey, this is something that I did wrong. Let me correct it. And next time it will try to make it better. So in this way, what's happening is you can easily figure out what the error is. And based upon that, you can keep updating the model. So this is same as somebody trying to do a math calculation. And every time they're sprouting random numbers, but based upon the data that they're getting close to the answer. Like, I don't know if you've played 20 questions and stuff like that. It's same as that. Like you get 20 questions to get nailed down to the correct answer. But in this model's case, we have so many more iterations. So it's not 20 questions at all. But yeah, in the end, you get a model that knows about the relationship between the input images that you have and the output expected labels that you have. So that's the supervised learning we have. Then we have unsupervised learning, or unsupervised learning in here. So on the right, we have unsupervised learning, where we just give it a lot of data. And based upon that, it tries to figure out different categories, different groups, clusters. That's the supervised learning, unsupervised learning. But this grouping them together of supervised as well as unsupervised learning together is called semi-supervised. And this became much more popular because what we wanted to do was train our model on a small set of data to say, in a small set, can I create a model which knows difference between cats and dogs, and like, let's say 10 different categories. And then I can give it a lot more images, like hundreds of thousands more images, and then it can easily do clustering. So since it already knows what a cat looks like, it doesn't really need to retrain on all the millions of other images of cats that I have. At that time, it can just do the clustering to say, I already know what a cat looks like. All of these images look like cats, so all of these images are cat. So that way, the training of the model became faster with semi-supervised, because you didn't lose a lot of complexity around just random clusters. So just to clarify again, unsupervised just creates clusters. Actually, I have a next slide. Somewhere later. Okay, so unsupervised learning creates just clusters, versus supervised learning creates 1:1 mappings. But when you combine them together, you get 1:1 mappings of clusters. So your clusters have proper name and proper definition, and that way, semi-supervised learning started becoming more of the norm, that everybody started using that. Then we started seeing generative AI. So generative AI, again, is a subset of deep learning, where we have these neural networks where rather than remember in these times, we are trying to predict an output. Actually, in here, we are trying to classify difference between blue and orange dots. What we realize that at the very end of the layer, the last layer, actually has a lot of information about what is blue and what is orange. So rather than asking it to predict or classify between orange and blue, why can't we just ask it to say, hey, can you tell me what blue is? And can you generate an example of blue? So essentially, at this point, we started saying, rather than doing classify, can you generate an example? And that's where generative AI started coming in, where rather than asking it to do the classification, we started asking it to do the generation. And that's where we started seeing a lot of new models that we are seeing these days, which are generative models. So just to clarify all the nomenclature again, AI is the whole field inside which machine learning is a way of doing things, and deep learning is just one more technique of machine learning. Within deep learning, we have different techniques as supervised, unsupervised, reinforcement learning. And then within deep learning, we have generative AI. Generative AI is powered by large language models. So all of those are in here. Any questions so far? Because this is all the terminology that we need to cover right now. And then we'll start going into deep. Good?
I had a few questions.
Yeah, sure. Go ahead.
Yeah, I had questions about the last layer, right? You were talking about how last layer determines, like, we can make it predict if it's gonna generate or not. Like, so how does this work in terms of code, and like what is the actual instance of it working in the last layer? Could you give an example more on that?
Writing code, maybe
Not write a code, but like, could you give more examples, like
Sure. So like a great example would be, so I'll tell you exactly how it actually came to being. So we were building like, not again, I'm saying we, it's not me, it's like the rest of the machine learning community. But we're building these models where, like a good example would be ResNet 50. ResNet 50 was a model for image classification. It was trained on millions of images by Google. They released the model out in the wild, and they added the ability to say, you can retrain this model with your own data. So I have an example on my GitHub where you can go in and you can add 5-6 different folders. Each folder has like hundreds of images of whatever you're trying to classify between. And then you can retrain resonant model and it will very quickly learn. So what was happening in that process is we take the last layer of the model, which essentially adds names to the values. So at this point, what it's doing is this is orange versus this is blue. That's all it's doing. And at that point is the name attachment to some understanding of what blue is or what orange is or what cat is. When we do retraining on those models, what we used to do is take that last layer out, replace it with our new learned data. And at that time, we assign new labels to those new learned abilities. Now, with generative AI, what we said was, rather than saying that assign new labels, let's just see what the output looks like. So in image cases, we just see what the output looks like. And for the text, we'll go through the whole example of exactly how text generation came into being. But for the images, it was just like, rather than seeing anything, rather than giving it a name, let's see what it ends up looking like. And if it doesn't end up looking like the thing that we want, then retrain it. So this was the era of GANs. We had generative adversarial networks where a network would generate something and another network would say, yes, it is the thing that I want it to be generating or not. And that's how they played cop and cat and mouse game. I'd rather say that cat and mouse game, where it was trying to generate something, the other model was saying, hey, it is correct or it is not correct. And in the end, it came to a point where the model really knew what a cat was like and it would generate the good images. It just wasn't as good as the current transformer models, and we'll talk about why that is.
Okay, thank you.
Okay, so as we talked about, there are two different groups of models. Now we think about models as two different groups. One is discriminative, where we are trying to classify or predict, or we are trying to cluster things together. In this whole process, it's learning the relationship between different features and labels and different groups of items. The other segment it has become now is generative AI, where we have the whole goal is to generate new data set. So what it's doing is it's still doing the relationship and understanding of distribution. But rather than doing the last layer of the relationship, we are just understanding what the distribution looks like, and then we predict those sequences back again. So still the prediction is happening. It's just rather than pointing it to a specific label or a specific item, we are just giving that out rather than pointing it to a label. So what does it look like? What do you need for it to work? For discriminative, you need data and labels, and you just train the model and it just gives you the label output. For generative AI, you need data and label to do some supervised learning, and then you add a lot of unstructured content so that it becomes unsupervised or semi-supervised learning, where it knows that, hey, there are some associations, and then I'm going to create these new clusters, and based upon that, I will learn more distributions. So you give it like, think of it as like you are making a model learn the basics of mathematics and computer science, and then once it knows that, then you give it a lot more content to learn. And rather than teaching it at that time, you just tell it to say, sit in front of a computer and do whatever you want to do. And that's how it learns to do computer science. So that's like essentially the part that's happening in here. So what's the secret sauce? How did it all ended up coming into being? So before we get there, let's talk about the biggest problem that was happening. So this is up till this point, 2013, we had models which were doing a lot of work in images and maybe some audio, because both of those are like easier to represent into numerical format. So machine learning models don't learn on the raw data, like images get translated into numbers. Waveforms of sound gets transformed into numbers as well. And then machine learning models can learn on those. But machine learning models can't learn on something that is not a number. And for text, it was a really hard problem because you can't take A, B, C and like convert it to 1, 2, 3, because as soon as you do that conversion, all the meaning behind the words is lost. So you can take a word and like if you assign the word a number, then the meaning is lost. And the other part important here is like, if I say, how did we get here? The order matters. It can't be just randomly did comes before how or we comes before how. It can't be just random order. So the order matters, as well as like the dictionary is not easy to do. So at that point, in 2013, we saw Google release this model called Word2Vec, where they were able to convert a word into the representation of numerical representation, where it was a vector representation. So what does it look like? So this ended up being called an encoder, where we have this sentence, the cat ate the mouse. The sentence can now be encoded into these vector formats. So this is the scalar value of the, just represents some random number in a dictionary. So the is just a random number in a dictionary, and like whenever we will use this conversion. So in this problem is translation problem. So let me show you the other side of this. This is the translation problem. So what will happen is the will get mapped to 1, and le, which is the French representation of that same the, will also get mapped to 1. So that way we know that 1 in English is the, 1 in French is le. So that way the mapping is 1:1. And then the second part is this directional arrow. That tells us that after the comes cat, after cat comes 8. And that way we have the complete information of the sentence is preserved, that each word is now represented into some value, which is also represented in the other language. But also along with that, we also have the directional input, which is what is the sentence structure looks like. So we have in here, the cat ate the mouse, and this whole sentence structure is in the decoder section, where we have the cat ate the mouse in French. This is the decoder, where here we learn all this association, and this decoder essentially translates that. So this started working really well, where this is like, just because we were able to convert text into a vector format, we were able to learn this. This is the supervised learning, where you have all this complete text, and this complete text is equal to this complete text in French. And 1:1 mapping, you get the answer. So this started working, but we started having problems. The problems were, where's the problems? Okay, problems are here. So this started working, and we came into this encoder-decoder architecture, where we had these encoders, we had these decoders, and this was our like very basic models that we started building on. But the problem was we needed some attention in here. Why did we need attention? Because of examples like this, where the example is black cat ate the mouse, but if you translate into French, the cat actually needs to come first. The black goes into the second argument in here. So at this point, just the relationship is, because vectors, they can only point in one direction. They can't point two directions. You can't have a bidirectional vector in here. The cat can't point back to say cat comes before black and then black goes after in here. So we needed some more information to be associated with these sentences. Along with that, we also needed sometimes, like if you are doing a larger sentence or a larger paragraph, or you're doing a question and answer kind of model, Q&A kind of model. At that time, we needed the information from like the beginning of the sentence. The information at the beginning of the paragraph is very important by the end of the paragraph. So we really needed all that information to make sense of what is happening. So that's where the attention came in, where remember that encoder model, we started adding some hidden state with each of the element. So we said, okay, this hidden state will contain all the other meta information related to this element. It could be position, it could be other meaning. Position is the easiest way to say like how it will become position into the conversion of like the after translation. So what we did was we added some hidden state. Think of it as just, so far the vector was a scalar value. So far at each point we had a scalar value and a vector direction. Now we started adding some more meta information along with that, and that ends up looking like this. So we have some more meta information along with each element. And this meta information essentially allowed us to pass this whole information to the forward layer. And when we are doing translation, we end up seeing that, hey, because we know that this is the order of the translation, cat needs to come first, black comes second, 8 is actually 2 words, a mange. So that's what the information is. And this whole information gets translated over here, and we get the proper conversion now. So we started seeing new conversions happen properly. But at that time, this works great. We saw new translation models being launched by Google, and they were working great, better than this generation where it wouldn't know the difference between black cat, and because it was very linear. So with attention, we started seeing better machine learning models on translation come in. But there was a big problem in here. The big problem was, depending upon the width of the context that you're looking for, like how much should you look ahead to get that attention? So in this case, we are looking ahead to the sentence end, and that's what we are using in this attention layer. So the amount of attention, what is happening is, every time we are trying to do a computation of what should go into the attention layer, is we have to do 1, 2, 3, 4, 5, 6, 7 computations at each level. So it was very serial process. So what is happening is, at this point, we convert black into a number, we find the next direction, and then a lot of serial computation is happening to figure out where does black come up into the French location or in the French translation. Then same thing is happening for the cat. And this serial nature caused these models to be really slow to both train as well as to evaluate. And mostly it was on training side, because anytime we increase the context window of the context length in this case, it ended up causing the models to become really slow to train and stuff like that. So we saw this happen in transformer architecture. This paper was released a few years ago, where the authors did a really good job at saying 2 things. They added this thing called self-attention and feed-forward. So what does it mean? Self-attention essentially said that at the time that you're completing, trying to find out the attention of this item, we don't really care about what the rest of the items are. So you only look for what your value is. And feed-forward said, rather than running this in serial order, let's run this whole process of attention in a parallel order. So that way, this first segmentation of generating the dictionary to the next item gets faster. So things become parallel. And when things became parallel, the whole process became much, much faster. So we came to this point of where our transformer models were essentially much faster to do the self-attention. So that way we knew exactly what element maps to what and all the meta information. And all of this was happening in a feed-forward network, which caused it to essentially be like in parallel. And that got this to a point where we could give it a very large amount of data, these models, and then started learning from those. And that's where we started seeing new translation models come in, where they were really good, where Google released this thing about like where they had 50 different language models learned between other 50 ones. And it's just like very good translation that was coming out of those models without doing a lot of specific training. And they were fast as well. So that was happening in transform models. That transform models, the core of that, with a lot of engineering on top of that, we are starting to see new kind of architectures emerge, where I'll start from the right side, encoder only. So the encoder only models are something that are used for most search-like applications. So Google uses this model called BERT for their search uses, where they encode all the information that they have into just encoded values. And then when the user types a search query, that search query gets encoded into encoded format, in the vector format, and then it gets sent to the query. What it finds is the answer along with the related area. Remember the clustering? So it finds that whole cluster and sends the result back. So at that time, that's why you see search results with not just one answer, but multiple answers. Because it with encoder only, there's no need to get the output. It just find the information, find the relative areas around that, and give it out. Then we saw decoder only models from GPT team, where their whole goal was to say, when users looking for something, let's synthesize some information. Their whole goal is to go AGI, and AGI means that the machine should be indistinguishable from the human on what it's trying to achieve. So at that point, they went with decoder-only model, where when you ask a query, it gets encoded into vector format, goes to the model, and model generates some output and gives it to you. And Google has this another model called BART, where they went with encoder and decoder format, where they are trying to do two things. One is, of course, generate an information, but they want to do it based upon some authoritative data. So that way the model goes in first to the encoder, finds some information, finds those clusters, passes those forward to the decoder layer, where it generates based some new information, some new answer based upon that layer, the encoded value. So what does it look like? It ends up looking like this, where for generative language models, the way model works is when you ask it to generate a sentence or generate an answer, or anytime it's doing any generation, it generates word by word by word. And for each word, when it generates it, it takes the first word, passes through the whole network, generates the next word, passes through the whole network, next. And that's how these language models are working. Any questions so far?
We do have a question in the chat. Actually, maybe this will be better suited for the end. So actually go ahead.
Okay, sounds good. So this is how language models are working. We also have generative image models. So just a quick break in here about like how generative image models work. Before we were doing the image-based training, to do that, we didn't really have a lot of data around image models. So what we used to do is we would take an image and we would try to create 50 different images out of that one image. And the way to do that was we would rotate it, crop it, add some noise, make some pixels black, make some pixels gray. And that way we would get like 50 more images from the one single image. And that's how you essentially augmented your data to, you really didn't have a lot of data, but you augmented your data to look like a lot of data. But that was the thing that we were doing for like figuring out how or what this image of a cat is a cat. Folks decided that, hey, if a model is able to remove or understand that there's noise in this image, can we do other way around, where we can give it just noise and ask it to generate an image? And that's where diffusion models came in, where it starts with just noise. And it says, okay, the user asked for, I don't know, avocado with a hat. So user asks for avocado hat or avocado with a hat. It tries to figure out how to do that, where it starts from a just all noise. And then it removes some pixel or changes colors of some pixels and says, hey, does this look like what user wants? If not, I'm going to keep redoing it. So it keeps redoing the same process. And over time, it comes to this result where it has the thing that user wanted. Doesn't matter how ridiculous it is. So those are generative image models, which are, if you haven't given it a try, there's a lot of new companies that are doing stuff like that. Stability AI, Midjourney, you will see those models as well. Of course, DALL-E is there as well. But DALL-E is doing it based upon transformer models, and this is diffusion models, so different types of models. So what are foundation models? We keep hearing this term about foundation models. So the way I like to think about it, or the analogy I gave, is for most of the dogs, if you think about what is a pet dog, they just really need to know a few things. Sit, come, down, and stay. If they know these things, it's a very normal pet dog. But you also have these special dogs where they are a police dog, where they need to go through special training for drug sniffing, or they are hunting dogs where they need to go through a different training, and similarly for guide dogs. So those are essentially fine-tuned models. So the way to think about it is like foundation models are these models which have some categories, some things within those models, like in this case, text classification, question answering, document summarization, or text generation. These things are within these large language models that are available. But if you want something more unique or something specific to your data, then you can retrain those models for your own use case. So what did we do so far? Just to go from the very beginning, for AI has been around for a long time. To build those models, the way we used to do that was write the whole program by ourselves. So in this case, we're trying to detect the difference between cat and a dog. We had to write the whole programming ourselves, the whole program on what does a cat look like, and all those things were being done in traditional programming. Then we came to the wave of neural networks, where we gave it examples of what is a cat, what is not a cat, and based upon that, the model now knows, is this a cat or not? Then came the era of these generative models, where we have, hey, this is a book, or these are the images of a cat. Go learn what is a cat like, and then tell me what is a cat. Or you can ask it a question, what is a cat? And that's what is happening with generative models. So how can you start using those? You see, in both of these two cases, the usage is very different, because you're asking for what is this a cat or not? And in this case, you're just asking it to what is a cat? Like, very much the use case is totally different. So why are people so excited about this? What is the reason around this? So what the biggest thing that has happened is the whole machine learning community can focus now on these one single type of model and one single type of problem. And once we put a lot of effort into that, we will start seeing new things happen. So for example, this one single model can be used for translation, sentence completion, Q&A, for writing code. And like, one single model is used for so many different tasks that you don't really need different expertise and different groups of data. Because think of this, before this, for translation model, you will have a totally different types of data. For sentence completion, you will have a totally different type of data set. The models will be different. When you train them and put them into production, there will be different kinds of management for both of those models. But with LLMs, it's just one kind of model. You give it a lot of data, train it, and then you have the same model being served for different use cases. The second better part with these models is these models can be fine-tuned with very minimal field data. So you can take a GPT-like model and train it to do some different language, and it will very quickly learn that, because it knows so much about languages that when you give it a new language, it can learn that as well. So they require very small fine tuning. And I'm giving the example of translation, but you can do the same thing of like text generation. And if you want to do text generation for university, some course languages that you're learning, you can give it the text for that information, and it will learn that new nomenclature, new ways of talking about things and stuff like that in there. Plus, as so much of the engineering and research is getting focused into this area, we are seeing the performance of these models getting more and more better and faster. We are seeing bigger models come in. We are seeing models being trained on all sorts of hardware. And as these models are becoming bigger and bigger, we are seeing new emergent behaviors come in. So one example on this is Facebook released a model called Segment Anything, where the model was supposed to segment an image to say, this is a person, this is a tree, this is a car. But what that model ended up learning, along with that, the model ended up also learning that what is a person. So you can ask it to generate a person as well. So not only it can classify between those, it can also generate those as a person or as an image. So these are like new behaviors that we are seeing within these models that will come in, just because they have learned so much about whatever information you're trying to make them learn. Now, how can you start using them? And like, of course, you can start using them right now. You can go to Bard or GPT and start asking questions. But sometimes they don't give you the right answers, the ones that you're looking for, or they make mistakes. So how do you make it better? This thing is coming out, which is better prompting. Don't rely on this too much, because after a few years, this will go away, because the models will get better at this. You don't have to ask better questions. The model will themselves get better at giving you the correct answers. So one of the examples is instruction tuning, where you give model instructions on how to do a thing, where you can say, hey, I'm going to tell you how to do mathematics. This is how you do mathematics. And now give me an answer to this question. Or you give it a formula for how to find pressure on, I don't know, if you give it a temperature conversion between Celsius and Fahrenheit, you tell it, this is the formula that you need to use for temperature calculation between Celsius and Fahrenheit. And I'm giving you a Celsius temperature, give me the Fahrenheit answer. So you give it instructions on how to do something, and then can do that properly. Then it has, just remember that these are not logical models. These are not mathematical models. Models don't do any of that. All it's doing is, when you're giving this extra information, is it's looking into the right place. because it has a large corpus of data that it can look into. And it also has some capability to do like simple math and simple computer programming. But if you give it information, then it can use that information to look into the correct locations. It's like you have access to a very huge library and you are just asking for something. And if you just randomly ask, it might go and look into fiction section rather than looking into physics section that you actually wanted it to look into. So with more information, more instructions, you can fine tune it to where to look. Similarly, we have dialogue tuning. This is more for Q&A use cases where people are using this for customer support use cases, where you can give it a lot of customer questions and answers and tell it to say, hey, your whole job is to be more helpful to the user. So even if you don't know the answer, try to give some links to the question, links to whatever user can read more about or wherever the information is. The last one, which is the most fun one in here, is chain of thought reasoning, where rather than you doing any of this task, you tell the machine to, or the model to say, this is somebody who tried this model called AutoGPT, where they essentially said that, hey, why can't the model itself learn to do better prompting? So you tell the model to say, hey, I want a website. But you also tell the model to say, anytime I give you a task, try to break it down into smaller tasks until you can reason that that task is small enough and you can do it actually. So what the model says, or the model does is when you ask it to say, build me a website, it says, okay, what are the things that I need? So it actually goes through the whole reasoning process and says, okay, I need a way to make web pages. How do I make web pages? I'm going to use JavaScript. Actually, maybe that works, maybe that doesn't. Maybe you should use HTML web pages. So it does the whole reasoning by its own and then gives you the outputs. It's costly, but it gives you generally much better answers than other prompting methods. But there might be time when the model has no idea about what you're learning. So in this case, let's say nuclear physics. I don't know if hopefully nobody's training models on nuclear physics, but let's say in case you needed a model on nuclear physics, what you can do is you can retrain a model or fine tune a model. And there are different ways of doing that. One of those is tuning. You can just take the model architecture. There are model architectures available in public. A lot of companies are using it where the model architecture is available. Data, you have either your own data or openly available data. You take that and train the whole model yourself. Or we have fine tuning. You take an existing model and you add in your data. You get a new model out of that, but it's fine tuned for your use cases. Then the third one is parameter efficient tuning method. This one is very interesting. And the best way to show that is with an example. But before we go in there one by one, tuning is same as if you wanted to build a house, you went to an architect and said, draw me plans for the house, and I'm going to build the whole house by myself. So you build everything in the house by yourself. Fine tuning is you have a house and you come in and you decorate it the way you want it to be decorated. So you put in the furniture that you want, the fireplace that you want, whatever that looks like. Parameter efficient tuning is you have the house, you have the furniture, everything else. You just change the decorations from time to time. When it's Halloween, you add the Halloween. When it's Christmas, you add Christmas decorations. What this does is, what this allows you to do is these parameter efficient tune models, you can add them on top of existing models. So you add these models in front of, let's say, PaLM model. So Google has PaLM models and you built a parameter efficient tuning model for your physics class. In that case, what this model will do is when a new query comes in, it will go through this model first and then to the bigger model. In that way, the answers that you will get will be much more relevant to the questions that you're asking. And you can easily fine tune or easily remove these models or easily update these models because it's not like, think of this, next time you wanted to do a decor, this is such a big cost in here. So if you wanted to change the home decoration every time between Halloween and Christmas, that would be such a big cost rather than just doing this, adding new hangings and removing some of the items from the page, on the home. That's the difference between cost and the effort that it takes. So parameter efficient tuning models are becoming much more the norm. The thing is, it's not available everywhere yet right now. So everybody's trying to make it work. So how can you fine tune right now? So we probably won't do that right now in the call, but on Google Cloud, you can do a fine tuning on a model itself where you will have to give it data on which you're trying to fine tune, and it has everything else for you. So this whole graph in here is essentially, it starts by getting the data. So it will pre-process the data. It will convert the data into the correct format that it needs. And then it will retrain the model on for you as well. And as it's doing it will also do the evaluation for you. And it will give you evaluation metrics on the left here. on TensorBoard, and it will also deploy the model for you. So it will do all of these processes for you. So all you have to do is capture your data, put it on a Google storage, so it can start doing the translation, fine-tuning. So what can these models do right now? These models have been out for a while. People have been starting to use this for all kinds of different use cases, and we are seeing these things have been around for GPT-2. So since GPT-2 came out, we started seeing marketing content and sales content being built on these models. More and more, we are starting to see new use cases come in. I'm very excited about biology and chemistry use cases. I have friends who are using multiple of these together. So Margaret, she's another machine learning GD, and she does fashion designing, where she will build the sketch form, then use the image models to color it and add some theme onto those images. Then she will use a 3D model to put those clothes onto a 3D model of a person, then and then have them walk on a ramp, and that whole thing gets generated into a video, and she adds the music on top using the speech-based models as well. So she uses like 4 of these together to build these 30-second clips, 40-second clips of a model walking on a rampway with music in the background, wearing her clothes, built with generative AI. And all of this is working right now. So yeah, you can start using these for your use cases. And with that is the end of the slides. Any questions? I'm here.
Thank you so much, Vikram, for your informative presentation. I know I especially appreciated the dog analogy for the fine-tuning.
Right.
But right before we jump into questions, I just wanted to send a little reminder about the attendance sheet that I have in chat. It's just how we measure how we can create the best events for our audience, if you guys have time to fill that out. And other than that, we do have a question in the chat. Can you provide any examples of real-life applications that utilize GenAI and other types of AI? I know that's something you just jumped into a little bit, but if you could go a little more.
Sure. So GenAI, I'll give examples that I use. So if you have ever searched for recipes online, it's very hard to find recipes online. And you have to first go through their grandparents' history, their history of the places that they moved into and all that stuff to get to the actual crux of it. With these models have been trained on all of this data that is available on the web. So what I have is now a thread that is going on with Bard where I ask it for recipes. It gives me exact recipe that I need, nothing extra in there, and it works really well. That's like one very simple, easy example that anybody can start using right now. You can do the other way around as well. I have seen people do this with GPT where they would take a picture of the items in their fridge and ask it to say, what can I cook today? So you take a picture of what are the items in your fridge. It will use that because it's multimodal now. So it will use the information to figure out what are the items that are in your fridge. Then it will do a search based upon that to say, hey, these are things that you can probably cook with this and give you recipes out of that. Very simple example, but I'm hungry, so I'm talking about that. The other side of this is code generation. I don't know if you're aware, but GitHub released this thing called Copilot, where you can start writing code and it will automatically write functions for you. In the beginning, I was using it a lot for comments only, but over time, I started using it for writing small functions, writing test cases for those functions. And now you can just like give it a whole module that you want it to write and can start doing that as well. And there are more features coming in. I think GitHub Copilot is being like, there's a conference that happens in November sometime, the GitHub's conference, and you will see more. And like the things that might be coming in is like, update this or convert this into different language. And you can already do some of these things like by directly somewhere else, but now these features are getting integrated into things that you already use, like your code editor. Google released this on workspaces where when we are on a call, not on Zoom call, but when we are on a Meet call, it will automatically record all the items, tag it to a specific user, generate a summary for people who join in late. And if you have a meeting doc related to it, it will even give you, before you join the call, it will give you what this meeting is about. It will give some summarized notes as well. So there's a lot of things that people are trying to figure out where can they start using it. And of course, there's a lot of toy examples as well happening where if you haven't seen this, the Stanford group did an example of, they created a simulated environment where they said, hey, we want to figure out if these gen models can actually do a simulation of Sims, if you have played a Sims game. So essentially they created Sims world and they said there's birthday of one person and the rest of they were like simulated people in that. And all of them were using GenAI. All of those simulated person is calling GenAI API. And they essentially ended up throwing a party for that person's birthday. So there's a lot of research going on in this. There's just like 2 days ago, I saw this called Table GPT or something related to that, where they're trying to use transformer architecture for figuring out how to do predictions for future. So everybody's just trying to figure out what they can do, where they can use it. There are amazing companies already out on this. Jasper is a company which was doing marketing emails. It's $1 billion company now. So there's a lot of things that are happening in this area. And of course, we'll see what more comes in.
A follow-up question to that, are there any ethical implications for humanity if we get too deep into mechanizing and automating all of these functions that humans would ordinarily do, such as displacing people out of jobs, etc.?
Yeah, so I think it's the same argument that happened when we replaced humans doing farming with tools, when we replaced humans moving cargo around with cars, and humans rather than typing out or doing all the calculations of math on a big sheet of paper with computers. So I think it's the same argument. Yes, it will probably, and very much so, it will displace some of the jobs. Some jobs won't appear, some jobs won't be there. But it will also probably, most probably, fingers crossed, will create new types of jobs, new types of opportunities for us. And hopefully the balancing act ends up giving us on a higher side after the end of this revolution that we are seeing right now happen. And I think it will, because think of this as now people are talking about this as a companion, and we're already seeing this a lot in coding, at least, where a lot of developers who use this as on the coding side, they can't get rid of it anymore. Like they don't want to write, nobody likes writing the documentation. And if there's somebody else, some program that can actually write the correct documentation for you, you are becoming so much more productive. And I think that's the thing that people should be more aware of, rather than the models taking away your job. It's the people who are going to start using these models. They're going to take away the job of 5 other people because they're that much more productive. So again, not taking away your job, but yes, the jobs will get changed. Things will change. Yeah, definitely a new form of AI programming. Yeah.
Any last questions anyone would like to add?
I had a question again.
Go for it.
Yeah, so I had questions related to self-attention that you did talk about during the encoder decoder stuff. I was wondering, like, is there more research going on in order to improve the encoder decoder, or like, is it like it has reached its maximum potential? Something.
No way it reached maximum potential. There's no such, in sciences, there's no max limit. It's simple as that. Doesn't
Yeah.
matter which field you're looking into. Sometimes we are blocked by different kinds of things, but it's never the max. Like a lot of machine learning research was blocked before GPUs came into being because we didn't have enough compute. So never think of that as like it's done. To give you an example, one of the things that happens, the example of the FIFA thing, remember that sentence of the FIFA is going to do something. In that example, what is happening is every time you ask for a sentence, what happens is we have to go through the complete network to get the next word out. But most often, we get the next word out, let's say 20% within the network or 50% within the network. We already have the next word, but we are still going through the whole network. Think of it as like every time you have to form a sentence, but to form that sentence, you have to walk through the whole library every time you have a new word. You're like, why do I need to do that? After like I got to 3 shelves and I got the answer, so I can come back and like go next time for the next word. So these are the kind of things that are happening right now. This is the self-attention being used on the production side, on the inference side. You will see some more things coming onto the training side as well. But essentially, that's what's happening is we'll figure out, hey, you don't really need to traverse the whole group. Or maybe something else happens where rather than creating this meta information along with the vector, maybe we can add all this information within the vector itself. And if we can do that, then there's no need for feed-forward neural network. Maybe the system goes much faster then. Maybe there's no serial computation. I don't know. There's so much. I'm not a machine learning researcher, so I actually don't know enough about what are the different avenues of research are going on. But I'm sure there's so much more going on. And if you are actually interested in that, there's a group called MLCC where they do a lot of these research paper readings where they will go in and they will read the research paper that's coming in, and you can ask questions about that as well.
Yeah, that was great. Thank you so much.
More questions?
Well, then that seems like this is a good place to wrap up. Thank you everyone for coming. And Vikram, thank you so much for your great presentation. It was great to have you.
Awesome. Thank you, everybody. Have a good day.
Thank you.
Thank you so much, Vikram.
Thank you. Thank you so much.
Bye.
Thank you.